Hello everyone, welcome back to the latest lecture session. In the last session we started discussing about how to remove the suspended solids that are in water, and were primarily concerned with those suspended solids which take too long to settle down, right? And then we looked at why it is that, or briefly looked at why it is that these particles do not come together, as in why is the system so stable. And okay, let me just look at that and we will go through. So we were looking at it in the context of water treatment, and after core screen and such, I am looking at suspended solids. Yes, and let's see, particles have an electrical charge. Yes, typically it's negative. We looked at the relevant reasons, I guess, right? Isomorphic substitution, natural organic matter being adsorbed onto the relevant particle. NOM, depending on the pH of solution, will typically be negatively charged. So the particle will also have negative charge. Yes, and now these negatively charged, what do we say, colloids, they won't come together, right? Why is it? You have this net negative charge here, net negative charge here. So these two particles won't come towards each other, or can't rather, because when they come towards each other, we see that there is going to be electrostatic repulsion. In that context, we came across one aspect that's relevant, right? Electrical double layer, and this stems from the fact that the particles have a negative charge, right? And we already looked at this. Let me go to the figure. So two layers, one is the adsorbed layer, which is also called the Stern layer, and it's of relatively less thickness. That's one aspect. And after this fixed layer or the Stern layer, you have a diffuse layer which forms beyond this fixed layer. And in this diffuse layer too, diffuse layer will have a net negative charge. That's one aspect. And more importantly, you can see that, its thickness, if I can say so, is relatively much higher compared to the thickness of the first layer. So this is the electrical double layer. Let's look at that in the picture. Please note that the reference in this slide is slightly different than what we looked at earlier, but the picture is more or less the same. Why I chose this is, here we have some sense of the particle or the distance from the surface here. Okay, so here we have the negatively charged particle. You can see the negative charge here, and because of that, the positively charged counter ions in the solution, the cations, are going to be, what do we say, pulled towards this particular particle, right? And that we are calling that as the fixed layer, or some people even call that the Helmholtz layer, but typically fixed layer or Stern layer, right? But please note that the thickness is pretty less. And then you have a shear, what do we say, zone, if I may say so, and then you have this diffuse layer. Yes, and this has a net negative charge, and that's why again the counter ions, which are the cations, will be pulled towards this particular zone. Yes, you will also obviously have some, what do we say, negative charge, but in general, because of the net negative charge, the cations will be pulled, or the counter ions, which are the cations, will be pulled towards it. So, and this is what we have, right? And we see that for this particular layer, let's say, from the shear plane, we see that it's called, what do we say, the potential is called zeta potential, right? And how can you measure this? Okay, fine, we won't go into this in detail at all, but you are going to apply a potential and then look at the potential in the shear plane, let's see, right? And then this context, or from this, we will be able to get this zeta potential, right? This zeta potential, which is mentioned out here. And why is this zeta potential important? Because typically it's, let's say, around 80 millivolts, right? And for this particular case, okay, let me try to draw it right here. So what happens when two particles try to come near each other, or what are the relevant aspects? We know that, let's say, this is the case, and this x-axis is the distance. Okay, this is the distance, and my negatively charged particle is here. Let's say this is 0 distance. Okay, and as the other particle, which is also negatively charged, tries to come towards this, it's going to experience a electrostatic force of repulsion. And repulsion, we are going to plot it in this location, repulsion, right? as you see, as it comes closer, it does increase, but maybe I should not have drawn it so close to this particular, what do we say, distance out here, right? We will look at the figure again later. We have a better figure, but for understanding, we will look at it now. So, maybe this is what it looks like. And again, this is due to the electrostatic force of repulsion. What else will come into the picture? As you come much nearer though, much closer, you are going to have van der Waals forces of attraction. It's like this, let's say, and as you can see, with distance it increases a lot, right? So, this is attraction, van der Waals forces of attraction, and here we have repulsion due to the electrostatic forces, let's say. Same charge, right? Negatively charged, and this is what the particle will encounter as the particle moves towards this negatively charged particle, and the particle moving towards the negatively charged particle. So, what does the net look like? What does the net look like? The net will look something like this. So, initially this as it comes in, then a maximum of repulsion and then attraction. So, as you can see, as the particle moves towards the, or one particle moves towards another negatively charged particle, what does it experience? It experiences a peak of what do we say, repulsion, let's say, right? Net of these two, repulsion and attraction, this is what we see, this peak. But after that, we see that attraction, R net is attraction. So, it pulls the particles together. But how do I see to it that the particles can come close enough so that the R net is attraction? Why is that important? If not, when the particles come closer together, you have this peak out here. So, the particles can't overcome this force of electrostatic or R net repulsion, let's say, right. So, how do we go about getting that done? In general, maybe I might have mentioned this in my previous session too. We look at, or we talk about charge neutralization, that's a general term. So, let us look at what are the aspects involved here. So, here different ways to go about it, but one aspect obviously is, okay, we look at this particular aspect, distance from particle surface A, I mean in Armstrong units, let us say, right, and another way to measure the distance. So, here if I decrease this double layer or the double layer thickness such that, this by what do we say, either increasing the ionic strength, typically by increasing the ionic strength of the water, then I can see to it that the particles can come close enough without being overwhelmed by that peak of repulsion. They will come close enough, and then the van der Waals forces of attraction will take over and the particles will come together. Now, these two smaller particles which I find difficult to settle will now form a bigger particle, right, form flocks or colloids, let us say two colloids come together, many more come together, flocks, and heavier bigger particle I will be able to settle them down. So, here we are talking about increasing the ionic strength such that this electrical double layer, the thickness decreases. So, that is the issue. So, for example, after adding what do we say, the relevant ions, maybe the R net, I am talking about R net, might be something like this, right. Why is that? Because the electrostatic forces of repulsion compared to the previous one, if I can get this right, maybe they are relatively lesser because of the higher ionic strength, but the van der Waals forces will still be the same. So, now as you see in the second case where we have the, okay, let me draw this, okay. So, this is the attraction, this is the repulsion after adding the what do we say, relevant coagulant such that the ionic strength increases, high ionic strength and low or usual ionic strength, let us say, right. So, here I decrease the what do we say, electrical double layer thickness, right, allowing and seeing to it that R net profile changes from this to this, right. So, that is what we have seen. Let us move on. And zeta potential, yes, and one aspect to look at is that the zeta potential, if it is 80 millivolts, it is difficult for the particles, typically it is around that. But if it is less than 20 millivolts, that is when you can have, or you will have coagulation, let us say, or that is when you will be able to destabilize a stable solution such that the particles can come together. That is something to keep in mind. And how do we measure zeta potential? That is already discussed in the last class, right. So, let us move on. So, okay, this is what we have. So, let us say this is my particle and this particle is coming towards this side. So, initially I have this repulsion force, and where is my attraction here, and this is my attraction. As it comes in, the R net is going to be something like this, repulsion is net, and now the particle can't cross this barrier, right. So, it won't come together. But after adding a coagulant such that the ionic strength is high and the electrical double layer is relatively less, now what is the profile here? The profile for the repulsion curve or electrostatic repulsion is this, and now R net is here. So, as the particle comes towards the other particle, you see that it does not undergo any net repulsion, or there is no net repulsion here, and as it comes nearer there is more and more attraction, and then obviously much more attraction. So, the particles come together and stay together. So, that is the aspect that we are trying to promote, right. So, we already looked at this removal process. Overall, what am I trying to do in coagulation? Again, no need to mug up definitions, there will be different people with different versions of their definitions. Here in coagulation, we are talking about the working definition. We are going to add chemicals or coagulants to the relevant particles, so that I neutralize the charge or decrease the thickness of the electrical double layer by increasing the ionic strength, so that the particle or the system is now unstable and can initially coalesce, right. And flocculation, the process of aggregation of the destabilized particles, as in now these particles are not stable, they are relatively unstable, right, and they can come together and form flocks, and that is what we have or we call as flocculation. Here we are destabilizing the particles, here we are seeing to it that, or we are talking about the particles coming together and forming flocks. Yes. So, coagulation theory, typically we talk about DLVO theory based upon the people who proposed it. So, before we go further, looks like we are going to look at the coagulant characteristics. So, one aspect is, as in whatever I add to the water should not be more toxic than what it is I am trying to remove. So, obviously it has to be non-toxic at the dose that I am going to apply. Another thing is, if it has a high charge density, as in we were talking about a particle here that is negatively charged, and thus it pulls these ions together, right. So, for the double layer thickness to decrease, let us say, I can add anions or cations, pardon me, such that the ionic strength will be high and electrical double layer will decrease. But if I add monovalent, as in Na plus or NaCl, which is Na plus and Cl minus, I will have to add a lot of it, right, to be able to achieve that ionic strength. Ionic strength is typically 0.5 times summation of Z square. Z is the charge on that particular particle or such, let us say Na plus. Okay, there is some other variable here too, but as you can see, at least one relevant aspect is going to be dependent upon the charge, right. So, again you are going to have the stoichiometry, concentration of the relevant compound too, which I am not writing here, but in general we certainly have this charge and to the power of 2. So, obviously, if you think of it too, the more charge that I can provide with maybe, if I should not say lesser mass, the more charge I can concentrated charge I can provide, then the electrical double layer thickness will be lesser at lesser dosage too, right. So, that is one thing to keep in mind, we will come back to this later. And it is insoluble typically in the neutral pH range, but again not of great aspect or great relevance, especially if we are talking about the different mechanisms of coagulation, let us say, right. So, let us move on. What are the types of coagulants? So, we will look at typically addition of coagulants such that you are going to have charge neutralization or form bridges between different particles. So, here we have two major aspects, one is charge neutralization, the other one is bridges. These are with respect to the soluble ones, and then if you have the insoluble ones, as in we know that if we add a compound to be at high enough concentration and look at the relevant pH and the ligand concentration, the compound will not stay dissolved, it will want to precipitate out, right, it will precipitate out. So, when it precipitates out, it will also see to it that it absorbs other particles of interest, and this type of removal is called sweep coagulation, right. So, three major aspects we will look at that. So, obviously charge neutralization, I am going to add those that have a higher charge, Al3 plus and such, or Fe3 plus. but the reason for adding Al3 plus and Fe3 plus is not only due to the high charge. Why is that? We will look at that later. But as you can see, in general, Al, aluminum, a lot of compounds with aluminum, right? And then with respect to iron, Fe ferric is Fe3 plus. Yes, again you can see that we are adding the relevant counter ion, but obviously for electroneutrality you will also have to have the anion, right? So that's something to keep in mind. We won't just have inorganic coagulants, we will also have some organic cationic coagulants. So we see them here, but in general they are not added as the primary coagulants. In general, primary coagulants you will typically add to neutralize this charge, and these organic coagulants you will add such that they act as bridges. What are these bridges and such? We will look at that soon, right? So coagulation mechanism, this is what we just discussed earlier. So what do we want? I want to see to it that the electrical double layer thickness is decreased or compressed. So that's what we have, right? And then van der Waals forces of attraction will take over and the particles will come through. So what is important here? As I mentioned, ionic strength and the charge of the counter ion are important. Well, this charge of counter ion, we just talked about it. So greater the charge density of the counter ion, right, then the electrical double layer thickness will be relatively lesser. So two aspects, ionic strength and the charge of the counter ion, let's say, right? And what is it that we are trying to achieve? We want to decrease this double layer, but to what extent? So looks like this model says that the van der Waals forces are relevant from about 1 nanometer, right? If the double layer can be reduced to less than this, then obviously we are going to have what is this, suspension or flocculating suspension, right? So that's something to keep in mind. Just try to understand this distance. Okay, so we have effects of solution concentration on double layer. So here is the potential. Here we are looking at the effect of concentration of the counter ion or effect of the increase in the ionic strength on the double layer. So here we have 60 milligram per liter, and you see the profile, the potential, let's say, right? Again, this is with respect to the distance. We are talking about the repulsion in general here, right? As we go towards the particle, it's increasing, yes. And if I increase the ionic strength by adding 600 milligram of NaCl, well, I see that this is the profile. And if I increase it tenfold or 1 order of magnitude further, I am increasing the ionic strength, and this is the repulsion that the particle will experience as the particle moves towards our particle of interest, right? So that's something to keep in mind. And let's look at the effect of charge on the double layer. So if I am seeing to it that I am adding a particle, let's say NaCl, and for Z3 plus, let's say it's FeCl3, meaning I am adding Fe3 plus, right? So you see with Z at 1 plus, same concentration, this is the profile, but with increasing charge, you see that it's something like this. Visually, you might not able to capture the information, but I believe we have a table and we will look at that. But in general, the charge will be such that 1 by 1 is to 1 by 1 is to 1 by 2 to the power of 6, 1 by 3 to the power of 6. So this is how charge will be affected. As in, you can calculate the ratios. I think it will be 1 is to 1.6 is to what, 0.14 or something. You can check that. But this is how charge will affect it, as in the concentration required will be in the range of, okay, this is not 100, I guess, right? So 100 is to 1.6 is to 0.14, but again, this is with respect to the charge raised to the power of 6. So that's the effect of charge. So you can look at the relatively less concentration of the compound required if you have higher charge, let's see, right? So that's something to keep in mind. Okay, this is the table that I was trying to look at. So the molarity, the concentration is 1 millimolar, right? And ionic strength is here, yes, and here is the charge, yes. So I am adding it at 0.001, charge is 1, so ionic strength is also 0.001. And this, okay, inverse will give me an idea about the thickness of the electrical double layer, right? So this is one measure of the thickness, fine. Okay, where did we see this picture earlier? Let me just point that out earlier. Okay, so we see this here, let's see, right? It is just giving us an idea about distance from the particle surface, let's say, right? Let's move on. Okay, and here with the same concentration but with charge of 2, right? Now what is the ionic strength coming out to be? You see that I mentioned that it's Z square, right? So that's why you see 2 to the power of 2, 4. So that's why you see 0.004, and then obviously 1 by K, or the distance, the electrical double layer will decrease. And if it's 3, again Z square 9. So you see that it's 0.009, even though the concentration is the same, ionic strength is relatively high, and then this particular electrical double layer thickness is relatively low. So if I increase the concentration from 1 millimolar to 0.1 molal, right, 1000 times or 100 times higher, I guess, right. So what do we have here? So again same aspect, 1:1, ionic strength is 0.1. Obviously it's much lesser. Why? The concentration is higher compared to what we have here. Concentration here, or the ionic strength, is much higher compared to what we have here, and for that concentration, if I increase the charge, right, and now I am going to have a higher ionic strength, and thus a much what do we say, lesser or much thicker electrical double layer. So you can now see the effect of the concentration and also effect of charge on the electrical double layer thickness. So that's something to keep in mind. So concentration required for flocculation, typical concentration seems to be 25 to 15 millimoles per liter. So obviously if it is divalent or trivalent, it's going to be relatively lesser, right? That obviously was illustrated when we looked at this particular table presented by or given in Crittenden et al., right? This is a good book if you are looking at water treatment, any aspect, right? That's one thing I wanted to mention. So adsorption and charge neutralization, let's look at the factors at play when we are trying to bring about coagulation. When we say hydrolyzed metal salts, what is it we are saying? Al3 plus is what I am adding, and I am adding it to water. So it's going to hydrolyze, the metal salt is going to hydrolyze. So pre-hydrolyzed metal salts and cationic polymers have a positive charge, right? So, okay, so it can be AlOH2 plus, AlOH twice plus, typically Al3 plus, right? But OH minus has a negative charge. So these typically have a positive charge, let's say. These are the various complexes that we are talking about. They destabilize the particles through charge neutralization. So this is something that can happen. Why? Here we have a positive charge, right? We are imparting positive charge. So the issue here to note is that Al3 plus, when you add it to water, will not stay only as Al3 plus, right? It's electron deficient, it's a metal. If you have a ligand, and what is the ligand here in this context? That's always available, that's OH minus, let's say, right? Electron rich and electron poor. Metal is electron poor, ligand electron rich. So they will try to form a complex, let's say, right? So you need a metal and a ligand. The ligand here, most common ligand in water is obviously OH minus. Why? H2O will be in equilibrium with H plus and OH minus. So Al3 plus in solution will not stay only as Al3 plus. It will form complexes, and as you can see, it depends on concentration of OH minus, for example, right? There will be an equilibrium between this complex and Al3 plus and OH minus. I am writing it in a simple form, right? So if I either change the pH or change the concentration of Al3 plus, the concentration of the complex will change, and also even the type of complex, as in will it be this one or one with no charge, right, or one with even a positive charge, will depend upon the pH. So these are the different complexes that aluminum can form with OH minus. Again, you don't need to go into detail, but what I am trying to say is when I add a metal, it won't stay as the free metal Al3 plus or Fe3 plus. It will form complexes with the ligands present there. So when we talk about charge neutralization, you see that even though I am adding something at 3 plus charge, in effect it can have 2 plus or so charge, or it can even have a negative charge depending on the kind of complexes that it is forming. And also If I add high enough aluminum concentration or ferric iron concentration or enough ferric iron, what's going to happen? It can even precipitate out of the solution. This is something that we looked at, co-precipitation or sweep coagulation, right? So, we will come back to that. So, it is not as if it is only charge neutralization, that is something I wanted to mention, right. So, here what is happening? Okay, this is, I guess, what is being mentioned here. So, we have a source of aluminum and you have Al3 plus dissociation into Al3 plus SO4 2 minus, and these ions tend to bind either directly to the particle surfaces, meaning adsorb, or to NOM on those surfaces. Please note that Al3 plus or can bind to the particles of interest, right, or as I mentioned, it can form a complex with OH minus, or it can also form a complex with the natural organic matter, which typically has a negative charge. So, these are the relevant aspects. Or if the particle itself has NOM adsorbed onto it, right, Al3 plus can also go there and neutralize the charge of this particular natural organic matter. As in, we know that the particle itself is getting charge. How is it? One of the ways is that NOM is adsorbed onto the particle, and you know that the relevant charge of NOM is imparted to the particle. So, if I add Al3 plus and this Al3 plus neutralizes the charge on the NOM by forming a complex with NOM, obviously the charge of the particle is also going to be neutralized, let us see, right. Let us see if we have a good figure. Okay, so this is what we see. So, typically we see COOH, right, but this H was released, that is what you see here, and that is why it has a negative charge. This is the typical structure of NOM, typical, let us say, and also OH, right, and that H seems to have been given out. So, that is why we have OH or O negative here, let us say, the charge is negative, and this Fe3 plus or Al3 plus that I add can go out here, and you can have complex between NOM and the metal, and thus neutralization of the charge. So, that is one aspect out here, coagulant combining with NOM, right. So, what is this about adsorption, charge neutralization? We spoke about it. So, when surface potentials are high, this is what we already looked at earlier. So, we can't really see to it that they come close together, right. So, repulsion is stronger as the particles come together, but by adding this coagulant such that I neutralize the charge, now the particles can come together and they can form these or start forming these flocks by colliding and sticking together. And in that context, I wanted to mention adsorption. Let me see if we have that here. Okay, let us look at this. So, colloidal particles in general, and after adding the coagulant, I destabilize the particle, and now they are relatively unstable and can come close together and form flocks. So, you can see the increase in the particle or size, overall increase. Let us say colloidal particles too small to settle out, and flock particles relatively bigger and they can settle out, but there are other aspects. Okay, so here we have adsorption and interparticle bridging. Until now we looked at charge neutralization, right. I have a charge on the particle and I am neutralizing the charge. As I mentioned though, we have other aspects. One is interparticle bridging, right, and adsorption. So, adsorption and interparticle bridging, when does that happen? Coagulant is a large molecule and it adsorbs on two colloids. I think I have a picture. Okay, so here you see that. So, here wet correct mixing and excessive mixing, we will come back to that. So, here is my polymer, let us say cationic or anionic or non-ionic depending on the situation. And so, what happens is this is a destabilized particle, earlier stable, now after charge neutralization or just adsorption you have this case, and now you have it, what do we say, adsorbing onto two different particles, and this thus forms a bridge, right. So, you have the bridge being formed. So, interparticle bridge is formed. Sometimes when you have excess dosing, you are going to have, what do we say, all the sites being taken up on one particle due to, what do we say, a lot of the coagulant or the polymer being added. That is not good, but depending on the type of what do we say, polymer being added, you can also have enmeshment. But again, this is something that you typically want to avoid, let us say, right, because you added too much. And if I do not mix it well enough, what is going to happen after some time? Let us say this is the initial case, my polymer has come and adsorbed onto one of the particles or one of the particles, and because of poor mixing it is not able to form a bridge with another flock. So, not flock, another colloid. So, what is going to happen after some time? It is going to be adsorbed onto the same, what do we say, colloid, and we have particle restabilization. So, leading to poor flock formation, though that is something to keep in mind, right. And what else do we have here? Okay. So, here I have excessive mixing, this is one issue. So, after I initially destabilize the particles, what do I want to do? I want to see to it that the particles come together and form flocks, though we will discuss this later. I wanted to mention it here because the figure has all the relevant aspects clearly illustrated here. So, what do we see here? Here let us say the flocks are formed, but after the flocks are formed, if I still mix it at what do we say, grade or such that the turbulence is very high, and for a prolonged period, what is going to happen? The flocks are going to break up. So, that is why we have it here, excessive mixing and correct mixing. So, the amount of energy that you are going to impart to the relevant solution is also important. We will look at that later. So, here we looked at some aspects, at least in this figure. What is it? Interparticle bridging due to the addition of cationic or non-ionic or anionic polymers. Yes. And also we looked at issues when we add a lot of what is this, the polymer, or when we add relatively what do we say, or we see to it that the turbulence is too high, or we do not mix it properly. What happens? The flocks do not form later. So, with that I will end today's session, but one aspect to note is that in today's session what is it that we looked at? We looked at compressing the electrical double layer by increasing the ionic strength. And what is a better way to increase the ionic strength? By adding, what do we say, particles that have a higher charge on them, right. So, we saw the effect on the electrical double layer at the same concentration for particles having charge 1 and particles having charge 3, let us say, we looked at that. So, in the context of destabilizing, we know that charge neutralization is one aspect, yes, and now we saw that or see that interparticle bridging is another aspect. So, interparticle bridging and adsorption, I will put it in the same vein. And the other aspect we are going to discuss later is some of these metals that I add do not stay in solution, as in the aluminum, it does not stay as Al3 plus, it also forms complexes, but even the complexes are soluble. But aluminum does not stay only as this dissolved metal or as the complexes. What will it do? If the conditions are right, it will start precipitating out. So, you will have a solid being formed and it will precipitate out. And this solid can enmesh, right, or see to it that other particles are entrapped. So, you are going to have what is called co-precipitation or sweep coagulation, but that I guess we will discuss it in the next session, and thank you for your patience.